Hello my friends and welcome back to the You Can Do TV channel.
Lucchini Mame Forge represents a benchmark in modern forging technology, integrating a full-cycle steel mill with advanced mechanical processing capabilities. Central to its operations are two high-capacity forging presses rated at 3,200 and 6,000 tons, enabling the production of large, high-strength components with consistent metallurgical integrity. The facility is equipped with state-of-the-art heat treatment systems to ensure optimized mechanical properties and structural uniformity across a wide range of steel grades. Precision machining operations are performed using advanced CNC equipment, ensuring tight tolerances and surface finishes that meet stringent industry standards. Each stage of production is monitored for quality, ensuring performance and reliability in critical applications. The integrated warehouse allows for efficient logistics and inventory management, supporting prompt global shipments. The Boast AR90 is a high-performance machine used for rough milling of crankshafts in the automotive and manufacturing industries. The process typically begins with the selection of the raw crankshaft material, which is secured onto the machine's workpiece fixture. The Boast AR90 uses a robust milling system to remove excess material from the crankshaft, shaping it according to the specified design dimensions. During the rough milling stage, the primary goal is to achieve the necessary rough shape of the crankshaft, typically involving the removal of large amounts of material. The machine employs high-torque spindles and advanced cutting tools that are specifically designed for heavy-duty material removal. The cutting tools are programmed to operate with high precision, ensuring that the material is removed efficiently while maintaining the integrity of the crankshaft's structural components. The Boast AR90 also features an advanced control system that monitors the milling process in real time. This system adjusts feed rates, cutting speeds, and tool paths to ensure optimal material removal without overloading the machine or tools. Additionally, the system helps in managing heat generation and vibration, which can negatively impact the milling process. This rough milling process is critical in preparing the crankshaft for subsequent machining steps, such as fine milling, grinding, and finishing. By effectively removing large sections of material quickly and accurately, the Boast AR90 ensures that the crankshaft is ready for precise final machining, meeting the necessary tolerances and specifications for high-performance engine components. Ultimately, the Boast AR90's capability to handle heavy-duty rough milling while maintaining high precision contributes significantly to reducing overall production time and improving the quality of finished.
Heavy forging work fills workshop number 4 at VSMPOA VISMA with constant activity, shaping metal parts that must endure extreme industrial demands. Production here revolves around coordination, timing, and controlled force. Operations are organized around large forging presses and auxiliary handling systems designed to move heated billets efficiently. Material arrives prepared for deformation, heated to working temperature, and positioned using cranes and manipulators that keep movement predictable. When everything lines up, the flow looks almost unstoppable. Forging itself applies immense pressure to form parts to require geometry while maintaining internal strength. Press operators monitor stroke force, alignment, and deformation stages to avoid stress concentration. That moment when the press closes always hits with a serious sense of weight. Between passes, parts are repositioned or reheated to maintain forming conditions without compromising structure. Once shaping is complete, components move through trimming and surface cleanup to remove excess material left from deformation. Dimensional checks follow to ensure parts meet production tolerances before advancing. There's no shortcut energy here, just steady discipline. Maintenance crews work alongside production, keeping presses, hydraulics, and power systems running reliably. Electrical and mechanical inspections prevent downtime in a shop where delays ripple fast. You can feel how one stalled machine could throw off everything. Planning and dispatch teams coordinate workloads, material flow, and schedules, ensuring the workshop keeps pace with broader plant demands. Finished forgings exit workshop number 4, ready for downstream processing across the VSM-POA-VISMA facility. All that force ends in parts that look calm, almost unfazed by what shaped them. Through structured coordination and controlled force, this workshop delivers forged components built for high-stress applications.
Greater impact force often results in more controlled grain alignment inside forged steel. Steel billets enter the forging line after controlled heating to forging temperature. Elevated heat increases plasticity, allowing the material to deform under force. The heated billet moves beneath a steam hammer or hydraulic press. Repeated impact or steady compressive force reshapes the block into a preform. High-energy deformation realigns the internal grain structure, improving strength and fatigue resistance. That strike lands hard. Wow! The force travels straight through the core. Between forming stages, operators reposition the workpiece to distribute deformation evenly. Excess material trims away during intermediate shaping. Progressive forging reduces internal voids and enhances structural density. Final forming passes achieve the required geometry before controlled cooling. Gradual temperature reduction stabilizes mechanical properties. The result is a forged component engineered for heavy-duty performance through directed force, thermal control, and mechanical shaping power.
How does a smooth steel disc become a functional gear? A gear cutting machine forms each tooth around the outer edge. The operation converts simple round steel blanks into functional gears used in heavy mechanical equipment. Circular gear blanks arrive at the workstation already machined with a center hole for mounting. Each blank slides onto a rotating spindle and locks firmly in place. The fixture holds the blank steady, while allowing controlled rotation during tooth formation. Secure clamping keeps the gear blanks centered, so every tooth space aligns evenly around the circumference. Loose mounting here would ruin the entire gear long before it ever reaches a gearbox. The gear cutting machine positions a cutting tool along the outer edge of the rotating blank. Instead of cutting the entire shape at once, the tool advances gradually into the metal. The blank rotates step by step through indexed positions. Indexed rotation allows the machine to repeat the same cutting position at equal intervals. The first pass creates a narrow groove across the rim of the steel disc. Once the groove reaches the required depth, the spindle rotates slightly and the cutting head advances again. Each new pass forms another space between future gear teeth. Repeated indexing transforms the smooth edge into a growing sequence of evenly spaced slots. The plain disc suddenly begins to resemble a gear pulled from the inside of a massive machine. Material removal continues around the entire circumference. The cutter deepens the grooves during successive passes until each tooth space reaches its final dimension. Equal groove depth ensures the gear will mesh smoothly with another gear under load. After the final slot is cut, the tool retracts and the spindle stops rotating. The completed gear releases from the fixture, and the next blank moves into position for cutting. Consistent machine movement allows identical gears to be produced in large quantities. Time-lapse footage compresses the sequence dramatically. Steel blanks appear, rotate under the cutter, and soon display full rows of gear teeth. Whoa! 1 second a featureless disc, the next second a fully formed gear ready for serious torque. Finished gears continue toward additional manufacturing stages such as heat treatment and surface finishing. Those steps strengthen the steel and prepare the component for demanding mechanical service. A simple round blank ultimately becomes a core element inside powerful machines.
Explore how a hydropower generator coordinates stator windings, bearings, and cooling systems to maintain long-term efficiency. Water-driven turbine motion transfers torque directly into the generator shaft. The rotor spins within the stator, creating a controlled magnetic field interaction. Magnetic flux density determines how efficiently mechanical rotation converts into electrical current. That invisible field carries serious force. No room for imbalance. Stator windings surround the rotor and capture the changing magnetic field as induced voltage. Proper winding layout stabilizes output voltage under fluctuating load conditions. Electrical current then moves outward through transmission connections. Bearings support the rotating shaft while absorbing axial and radial loads. Bearing stability directly influences generator lifespan and vibration control. Brackets and structural frames handle mechanical stress generated during continuous rotation. Ventilation channels guide cooling air across windings and core components. Heat removal protects insulation systems and maintains operational efficiency. Thermal management prevents performance loss during sustained generation cycles. Through balanced magnetic fields, mechanical support, and cooling control, the hydropower generator sustains reliable energy production across long service intervals.
Large steel frames weighing several tons form the structural base of a horizontal boring machine. Large cast and welded frames arrive first and move toward machining centers that cut guide surfaces, mounting faces, and spindle housings. Accurate alignment at this stage determines how smoothly the spindle will travel through metal during real cutting work. Machined parts proceed to subassembly areas where spindle units, gear drives, and sliding tables come together. Hydraulic and lubrication systems install next, supplying controlled motion and long operating life for moving sections. A massive frame slowly gaining shafts, motors, and rails almost feels like a mechanical skeleton turning into a living machine. Electrical cabinets, control units, and measurement systems integrate into the structure, allowing operators to manage positioning and cutting parameters. Precision grinding follows on key surfaces to refine geometry and improve stability during boring operations. Suddenly the machine stands complete, towering and ready for metal cutting tasks. Wow, that transformation lands fast. Deep grooves on crankshafts and heavy rolls appear quickly once a heavy-duty machining tool begins cutting dense metal. Each contact point determines chip flow and tool life during these demanding operations. Grooving tools shape crankshafts and cast iron rolls. Metal curls peel away like tight springs. Piling beside the cutter, that spiral stack grows fast. The build sequence of a rolling mill machine reveals how rollers, drives, and frames combine into metal-forming equipment. Steel frames move onto machining stations that cut bearing seats and mounting surfaces. Accurate alignment here controls how smoothly heavy rollers will spin during metal forming. Shafts, gear drives, and roller housings come together. Huge rollers sitting side by side look ready to squeeze steel like dough. Whoa, that pressure idea hits hard. A bevel gear tooth looks compact and simple, but shaping that curved geometry requires complex motion from a 5-axis milling machine cutting hardened alloy steel. The machining sequence forms the spiral bevel gear used in drive shaft systems. A gear blank made from SCM 440 alloy steel enters the machining stage with hardness around 34 to 36 HRC. The part mounts on the table of the 5-axis milling machine, where simultaneous axis movement positions the cutter along the curved tooth path. Multi-axis motion allows the tool to approach the gear surface from angles impossible for standard milling setups, and the blank already hints at the future gear hidden inside the metal. The first operation forms the main groove between teeth. A cutting tool labeled SIW CREBMR5 travels across the gear blank while the machine coordinates rotation and tilt angles. Cutting speed reaches about 80 meters per minute, while the tool advances gradually into the steel. Controlled feed movement prevents excessive load on the cutter during this early groove shaping stage. Next, semi-roughing passes shape the right side of the tooth using a taper ball end mill. The tool moves at more than 5,000 revolutions per minute while removing material along the curved surface. Small compact chips appear during cutting, a sign that the milling conditions remain stable. Oh, that steady stream of chips confirms the tool engagement remains balanced across the spiral surface. Another semi-roughing pass forms the left side of the tooth profile. The same cutter geometry follows a mirrored tool path to maintain symmetrical tooth geometry. Balanced removal on both sides keeps the tooth centered along the gear pitch line. Further machining refines the groove area between teeth using a controlled step depth. After the semi-roughing operations shape the structure, finishing tools enter the sequence. A corner radius end mill completes the bottom of the tooth and then travels along the involute surfaces on both sides. Finishing passes smooth the steel surface and produce the glossy appearance required for gear contact zones. The metal suddenly carries the curved lines expected from a fully formed bevel gear tooth. Several tool sets operate on a multi-function horizontal press brake, allowing plates, pipes, and bars to bend under controlled force. A horizontal press frame holds interchangeable tooling along its working axis. Operators select punch and die sets depending on the forming task. The HP20 configuration uses a radius punch paired with a V-die positioned at about 90 degrees with a 50 mm opening. Steel plates, made from St. 37 material, slide between the tools before the press arm advances. Correct punch-to-die alignment determines whether the bend angle forms cleanly across the entire width of the plate. A flat plate entering the machine looks completely ordinary. Give it one push from the press and a structural part suddenly appears. The press ram moves horizontally rather than vertically, pushing the punch through the workpiece toward the die opening. Material thickness around 8 mm bends into controlled angles under steady force. Horizontal movement gives the operator better access when forming long parts or unusual shapes. Tool changes allow the same machine to perform additional forming operations. A smaller V-die set with an 85-degree opening works together with a bolt punch designed for thinner steel pieces. Plates only 2 mm thick feed into the die slot where the press arm forms accurate bends. Smaller die openings concentrate force along a narrow line, which allows thin material to bend without distortion. Another configuration uses a square punch combined with a multi-V die block. The operator rotates the die block to match different bending angles. Steel strips around 30 mm high receive tight angular bends across their length. Rotating multi-dies expand the machine capability without replacing the entire tool assembly. Whoa! One machine suddenly handles several bending setups without moving the workpiece to another station. Heavier forming operations use larger press models in the same series. A ring-forming die shapes circular components from thin steel strips, while a wide radius bending tool curves thick ST52 plates into large arcs reaching hundreds of millimeters in radius. Large radius dies distribute force over a wider area so thick material bends gradually instead of forming sharp kinks. copper bus bars enter another specialized station equipped with precise bending tools. Flat copper bars bend into controlled angles required for electrical distribution assemblies. A different tool arrangement produces Z-shaped bends along the bus bar length. Throughout the forming sequence, automatic backgauge positioning controls where each bend occurs along the material. Consistent backgauge positioning allows repeated parts to match dimensions across entire production batches. Straight stock enters one side of the press and leaves shaped into parts ready for assembly lines. A tower crane may lift tons of material high above a construction site, but the real limit of the machine often hides in its service life rather than its lifting power. Steel sections form the main tower structure, assembled from modular mast segments. Each section connects through reinforced joints designed to distribute load throughout the vertical frame. Strong connections along the mast prevent bending stress from concentrating in one location. Segment by segment, the tower grows upward until it reaches the height required for lifting operations. Once the mast structure stands in place, the slewing unit mounts on top of the tower. This rotating platform supports the working arm and counterweight system. The horizontal jib extends outward to carry lifting loads, while the rear counter jib balances the crane during operation. Balanced load distribution keeps the rotating structure stable during lifting cycles. The hoisting mechanism then enters the system. Steel cables wind around the drum of the hoist winch, guiding the hook block up and down along the jib line. Controlled lifting speed prevents excessive mechanical stress on the hoisting components. Yet lifting capacity alone does not determine the long-term reliability of a crane. Equipment repeatedly working beyond its intended service life gradually accumulates structural fatigue. Long-term durability depends on respecting the operating limits designed into each structural component. So the crane may appear strong every day, but internal fatigue quietly grows through years of operation. Excessive overload can cause immediate mechanical failure, but long-term misuse creates a more subtle risk. Structural components experience repeated stress cycles across thousands of lifting operations. Understanding this balance between lifting capability and service duration allows a tower crane to operate safely across demanding construction environments. Five different machining operations shape hardened alloy steel using the Coil Mill 390 milling cutter, demonstrating how controlled damping supports stable milling and higher metal removal rates. A cutter equipped with size 11 inserts engages the EN34 CR906 alloy steel workpiece during shoulder and face milling. Cutting speed reaches about 180 meters per minute, with a feed of 0.12 millimeters per tooth, while the cutter removes a 2 millimeter depth of material across a 15 millimeter engagement width. Stable damping inside the tool holder limits vibration that normally appears during aggressive milling passes. The next operation widens an existing bore through helical interpolation. The same Coil Mill 390 cutter follows a spiral path around the hole while gradually increasing its diameter. Cutting speed rises to 270 meters per minute, and feed increases slightly to 0.15 millimeters per tooth. Helical tool motion spreads cutting forces along the circular path rather than concentrating them in one direction. Slot machining follows with keyway milling along the surface of the steel component. The cutter advances across a 25mm engagement width while maintaining a 2mm axial depth. That groove appears in seconds once the cutter tracks the programmed path. A different insert size then performs plunge milling. The cutter moves vertically into the material while feeding at about 677 mm per minute. Plunge milling distributes cutting force along the tool axis, allowing deeper penetration into tough alloys. The final stage applies helical side milling to refine the machine's surface. Cutting speed climbs to 300 meters per minute with shallow radial engagement. Damped tool technology keeps vibration under control throughout the high-speed finishing pass. A rigid aluminum slab suggests slow machining work, but this full automated slicing saw converts it into uniform plates with surprising speed. That moment, the first plate slides away from the slab. Hold on, the transformation already happened. A large aluminum cast slab arrives at the infeed section of the full automated slicing saw system. Mechanical handling equipment positions the slab and aligns it along the cutting path. The slicing saw advances through the metal using a rigid blade arrangement designed for thick aluminum material. Each pass removes a full plate with steady thickness, a detail that keeps downstream machining predictable. Separated plates move forward through a brushing station that clears chips left from the sawing stage. Those tiny aluminum curls pile up quickly. Apparently, the saw never runs out of work here. Removing these fragments keeps the plate surface clean before further handling. A weighing unit measures every plate immediately after brushing. The system records the mass to confirm production specifications and maintain traceability. That quick measurement step quietly verifies the whole cut without slowing the line. Next, a vacuum handling manipulator lifts each aluminum plate. Suction pads secure the metal surface and move the plate to the next station without mechanical clamps. The automated arm places the plate precisely for marking and identification. A paint marking system prints production information directly onto the plate surface. Automatic labeling equipment attaches identification tags for storage and logistics. Suddenly, each plate carries its own identity, almost like a passport for the factory floor. Meanwhile, aluminum chips generated during slicing travel toward a compacting press. This equipment compresses loose chips into dense blocks suitable for recycling or transport. Metal scrap turning into compact blocks. Nothing goes to waste in this corner of the plant. By linking slicing, cleaning, measuring, handling, marking, labeling, and chip compaction, the full automated slicing saw line forms a complete plate production workflow for aluminum materials. Follow the AMI step-ladder production system to see aluminum rails and steps assembled into a folding ladder ready for real climbing tasks. Raw aluminum profiles arrive first and move through cutting stations that size rails and steps to exact lengths. Sections slide toward drilling units that open holes for rivets and hinges along both rails. Step plates move through another station where edges are shaped and surfaces prepared. The rails line up with the steps on an assembly fixture. holding each component steady while fasteners secure them together. A ladder slowly appearing from separate strips of metal carries a strangely satisfying sense of order. Riveting tools clamp down, locking every step firmly between the side rails. The structure then passes through hinge installation. Folding brackets connect the two ladder sides, creating the familiar A-frame shape used for climbing and standing tasks. One quick glance already reveals the balance that keeps a person steady several feet above the floor. Surface treatment follows to improve durability. Aluminum parts may pass through brushing or finishing equipment that smooths edges and prepares the metal for protective coating. The nearly finished ladder moves through inspection, where alignment, step spacing, and folding action receive attention. Suddenly, the pile of metal parts has turned into something ready to hold real weight. Approved ladders leave the line ready for packaging and shipment. A stack of fresh concrete blocks appears in minutes from the ELKOBLOCK 36M multi-layer concrete block-making machine. Dry concrete mixture arrives from the mixer and spreads evenly across the mold box placed over a production pallet. The movable vibrating table drives strong compaction through the mix while the tamper head presses downward. High vibration force pushes air outward and packs the material tightly inside the mold cavities. Hydraulic motion lifts the mold frame, while the pallet carries the new layer forward. Another portion of mixture drops in, and the cycle repeats, allowing multi-layer production in one stacking sequence. Stacking pallets rising one layer after another feels like watching a concrete bakery tray fill up. Sensors and control systems coordinate vibration levels, pressing force, and pallet movement. Melt aluminum, forge structural shapes, machine the surfaces, and assemble components to produce steering and suspension parts. Aluminum raw material enters melting furnaces reaching around 730 to 750 degrees Celsius. Molten metal then feeds extrusion presses capable of more than 300 tons of force, forming strong profiles for later machining. Controlling temperature and pressure at this stage determines the strength hidden inside every finished component. Forging machines apply up to 5,000 tons of power to shape structural pieces such as ball joint housings. After forging, parts pass through crack inspection systems that use fluorescence to reveal structural defects. A glowing inspection line exposing invisible fractures feels almost like metal revealing its secrets. Approved pieces move into T6 heat treatment, improving hardness and mechanical durability. CNC machining centers then cut surfaces, drill holes, and refine geometry with tight dimensional control. Shot blasting cleans the surfaces before oxidation treatment protects the metal against corrosion. One rough forging gradually transforms into a smooth mechanical part, ready for assembly. Wow, that change happens fast. Assembly stations install ball seats, clamps, and riveted connections. Grease filling follows to support joint movement. Final testing measures swing torque, hardness, tensile strength, and durability cycles before components move to storage and distribution.
Ball valves up to 1 inch are produced in sequence on the MACOD transfer-type ball-making machine. An NC bar auto feeder delivers raw material into the cutting unit, where blanks are prepared to uniform length before entering the transfer system. Auto loading through the linear feeder positions each piece precisely for sequential machining. At Station 1, hole drilling establishes the internal passage required for flow control. The part then advances to Station 2, where milling refines the external geometry to support later finishing. Station 3 introduces slotting, forming key features needed for valve assembly alignment. Seeing all 3 operations handled without stopping feels like pure efficiency in motion. Station 4 performs mirror turning and chamfering, defining the ball surface that directly affects sealing performance. Surface quality is controlled through consistent toolpaths as parts rotate under steady feed. This is the stage where sealing reliability is decided, not guessed. Once machining is complete, auto unloading removes finished balls from the line and clears space for the next cycle. The transfer-type layout keeps throughput steady while reducing manual handling. Everything moves forward like the machine already knows what comes next. The result is an automated ball-making process focused on repeatable geometry, stable output, and production-ready valve components.
Manual fitting is often associated with bearing production, but the automatic bearing assembly system integrates ring feeding, ball insertion, and cage locking through a fully automated sequence. Ring feeding units align inner and outer rings into indexed positions. Consistent orientation at this stage determines downstream dimensional accuracy. Outer rings pass through measurement stations, followed by inner ring gauging. Diameter verification ensures correct internal clearance classification. Data from both checks directs the ball selection module. Ball grading directly influences load capacity and rotational stability. Joining stations pair matched rings, creating the bearing channel. Ball insertion heads distribute rolling elements into the raceway. Uniform spacing prevents contact overlap during operation. A cage fitting mechanism positions the retainer over the ball set. Cage alignment maintains separation under high-speed rotation. Riveting units secure the cage structure, locking components into a complete bearing assembly. Automated coordination reduces assembly variation across large production volumes. Final inspection confirms dimensional compliance before packaging. Bearings ready for industry, medicine, chemistry, and food processing. That coverage spans everywhere.
Engineers and machines coordinate at BUZULUK to refine piston rings for multiple engine platforms. Production relies on 4 heat treatment ovens, including 2 2-ton units and 2 1-ton units, preparing material for accurate forming. Machining follows in a free-shape condition, allowing the ring profile to match performance requirements defined by engine parameters. That free-shape stage decides how the ring behaves long after it leaves the line. Surface treatment then becomes the focus, starting with hard chrome plating and modified variants such as chrome ceramics. These treatments introduce channels filled with hard particles to extend durability in modern engines. Molybdenum spraying and nitriding are applied to meet different operating demands. You can almost feel how much work those surfaces are expected to survive. Development continues into advanced solutions using nitriding combined with PVD coating, depositing thin hard layers directly onto the ring. Finished designs move to test engines, where performance is verified under real operating conditions, That testing phase feels like the final gate before trust is earned. BUZULUK maintains thousands of drawings, supporting piston rings for small compressors, trucks, tractors, generators, and more. With most output exported to global markets, the process emphasizes repeatable quality, material development, and steady improvement across production cycles. High-speed aluminum machining pushes tools to reveal their true limits, and this Kennametal setup makes that visible immediately. A solid block of A383 cast aluminum is secured as face milling establishes a flat reference surface. PCD cutters remove material at controlled depth and width, keeping the cut stable while feed rates stay aggressive. That wide pass clears stock fast without loading the tool edge unevenly. Drilling follows, opening precise holes through the aluminum with steady feed per revolution. Chip evacuation remains consistent, preventing recutting inside the hole. Those clean exits matter more than they look once tolerances stack up. Full slot passes then cut through 3 aligned holes, pushing the tool engagement to its limit while maintaining control. Pocket milling reduces material step by step, using shallow radial engagement to manage heat. This is where PCD edges quietly earn their keep. Helical interpolation creates circular features with smooth wall finish and controlled entry. The tool spirals downward instead of plunging straight in, easing load transfer. That motion feels calm for how fast material disappears. Final full slot moves open the pocket completely, leaving sharp edges and uniform surfaces. One clean cycle, no hesitation.
Tire casings arrive at the Hennice Retread facility in Cleona, Pennsylvania, where trained specialists perform a hands-on visual inspection. They check for rocks, nails, screws, and other foreign objects. The care taken here really makes you appreciate how much goes into keeping every tire safe. Electrical testing identifies punctures or hidden damage invisible to the naked eye, and all visible injuries are marked for repair. Each casing is tracked with scanners throughout the production line to meet customer specifications. Next, casings are loaded into the shearography machine. Vacuum pressure is applied while lasers scan bead to bead. Cameras create animated visuals of any abnormalities. Tires that cannot be repaired are rejected. The casings are then mounted on the buffing machine and inflated to operational shape. The operator resurfaces the tire according to the manufacturer's parameters, removing damaged material caused by debris, punctures, or rust. Skiving prevents defects from worsening. This part is crucial for the retread to last. Cement is applied to the damaged areas, preventing oxidation and providing a tacky surface for the uncured rubber. Large injuries, including bead, crown, and shoulder damage, are repaired using bandag-specific materials, creating a permanent bond for long-lasting performance. That repair process turns what could be trash into something reliable for thousands of miles. A thin layer of uncured cushion gum is applied evenly across the crown to fill skive-outs and prepare for the new tread. Using the bandag builder, the technician carefully applies the uncured tread, ensuring it is straight, centered, and spliced correctly. The tread is stapled to maintain placement during curing, then stitched to remove trapped air. The tire is enclosed in an elastic envelope, sealed at the beads, and vacuum tested. Curing chambers apply precise heat and pressure, permanently bonding cushion gum to the new tread. The low temperatures used allow these tires to be retreaded multiple times, which is kind of wild. Final inspection ensures all customer specs are met, followed by a fresh coat of weather-resistant paint and a label detailing the retreaded tire's information. Feels satisfying knowing the tire is ready to hit the road safely.
Operators maneuver the Nye EXT200 through rows of vehicles, positioning the hydraulic arm for precise engine and transmission removal. The EXT200's hydraulic arm can lift engines up to 2,000 pounds with stability. The rotation flexibility of this tool allows separation with surprising ease. Once aligned, the EXT200 lifts the engine cleanly from the chassis, while minimizing damage to surrounding components. Hydraulic controls respond instantly, giving the operator fine control over delicate movements. Operators can rotate the arm incrementally to access hard-to-reach engine mounts. That grip strength looks like it could handle much heavier engines than the ones shown. After extraction, sheet metal parts are sheared efficiently, using the EXT200's corner post blades. Somehow, it handles these sharp angles without missing a beat. The shear blades are adjustable, allowing precision cuts on various vehicle models. Wiring harnesses, interior panels, and other non-metal components are carefully picked and sorted into designated bins. The machine's full 360-degree rotation enables detailed access to difficult-to-reach areas, simplifying the otherwise tedious disassembly. Watching the EXT200 isolate each component makes the process look deceptively simple. Throughout the yard, multiple units may work in tandem, sorting scrap by type and size. Containers fill with steel, aluminum, and other metals, while plastics and composites are separated. This kind of organization ensures maximum efficiency and reduces downstream sorting errors. The operator can adjust the shear blades for precision cuts, sniping frames, or small corner posts without disturbing the main chassis. Hydraulic feedback ensures smooth lifting, reducing the risk of accidents. The EXT200's combination of strength, dexterity, and control almost feels like having an extra set of human arms. As each car is stripped, the machine seamlessly moves to the next, keeping the workflow continuous. By the end of the day, a pile of sorted scrap stands ready for recycling. Feels like the EXT200 doesn't pause for a second, every move is pure efficiency. Engineers monitor the hydraulics and blade performance to maintain reliability throughout repeated cycles. Operators receive visual feedback through an onboard display to track each task. The EXT200 reduces labor time per vehicle by approximately 40% compared to manual methods. This attachment proves invaluable in modern scrapyards, making engine extraction, component removal, and material sorting faster, safer, and more organized than manual methods alone. That sniping action on corner posts is surprisingly satisfying, almost like sculpting with metal. Every movement is deliberate, from grasping the engine to dropping sorted metal into the appropriate bin. Safety protocols are maintained throughout, ensuring the operator remains protected while maximizing output.
Thousands of pleated folds form daily inside filters produced by an oil filter production line, full auto. Metal shells, filter paper, and sealing parts combine into compact filtration units used in combustion engines. Steel sheet coils supply the outer housing material. Sections feed into a forming station that presses circular cups from the flat sheet. Each cup gradually stretches deeper with repeated forming strokes until the cylindrical filter shell reaches its final height. Stable forming pressure keeps the wall thickness consistent across the entire housing. Next, the shells move toward a trimming and perforation stage. The upper edge receives a clean trim, while machines punch inlet holes that allow oil to enter the filter body. Uniform hole placement ensures balanced oil flow once the filter enters service. Parallel to the metal housing line, rolls of filter paper feed into a pleating system. The machine folds long strips into repeated ridges that expand the filtration surface. Pleated paper dramatically increases the contact area available for trapping contaminants. Whoa! Those narrow folds pack a surprising amount of filtering surface into a small cylinder. The pleated paper section wraps around a central support tube. End caps secure both ends of the paper cartridge, locking the structure into a rigid filtering element. Adhesive bonding seals the edges so oil cannot bypass the filtration media. Sealed edges force every drop of oil through the filter paper instead of slipping around it. Assembly units then insert the finished filter cartridge into the steel shell. A threaded base plate joins the housing and forms the mounting interface used during installation on an engine. Thread alignment here determines whether the filter seals properly during engine operation. Rubber sealing rings install at the base plate to prevent oil leakage once the filter is tightened onto an engine block. The completed unit travels through a crimping station where the shell edge folds securely around the base plate. Final inspection stations verify structural assembly and external condition. Consistent automated handling allows large batches of identical oil filters to leave the production line ready for engine maintenance work. Manual winding placement may look workable, but large stators depend on the 42 big motor coil inserting machine to load coils efficiently. Prepared stator cores arrive at the insertion station after insulation layers line the slot walls. The stator frame locks into a holding fixture that stabilizes its position during insertion. A fixed stator position keeps every slot aligned with the insertion tooling. Preformed copper coils sit in a loading tray above the stator. The 42 big motor coil inserting machine guides a pressing head downward, pushing coil groups into the stator slots at the same time. Simultaneous insertion reduces handling time compared with loading each coil individually. Copper loops slide neatly into place, almost like fitting a bundle of springs into narrow channels. Guiding plates control the coil shape while entering the slots. These guides prevent the copper windings from spreading or snagging along the slot edges. The press head retracts once all coils settle inside the stator. Operators remove the assembled stator and prepare it for the next stage of motor production. Suddenly, the empty metal core looks ready to generate power.